Let's review the equations of free fall. There are three equations here. And obviously, they're valid for falling object. It means if you drop something, or if you want to shoot something downward, it should follow these equations. And apparently, there is no problem. And based on these equations, you can predict the height traveled by your falling object, or velocity, or, for example, estimated time for traveling a specific height. It's possible to predict these values. But right now, I want to talk about something different. Imagine I have a hammer and I have a feather. If I want to drop these objects from the same height, so what do you think? And what happens? If I release it from the same height at the same time, which one is faster? Hammer or feather? And according to these equations, they should be the same because both of them are falling objects and they should follow these equations. But you know, there is a big difference between the feather and the hammer. And of course, hammer is much faster rather than the feather. Why do we have this equation? Why do we have this condition? And at that moment, these equations are not valid for the feather. So what happens? And let me show you something, or let me show you a picture from the textbook. And it's not bad to look at this figure. Give me a second, please. Look at this figure. This person would like to drop two different objects. The first one is brick and the second one is feather. Or maybe, for example, this experiment, you have feather and hammer. So you have the same experiment. There's no difference. Okay, obviously, you know that brick here for this experiment, it is much faster rather than feather. Or for example, if you want to do experiment with the hammer and feather, hammer is much faster. Why do we have this situation? And the feather will not follow those equations. Actually, that's the very important answer here. And this is the key difference between feather and brick, or feather and hammer. If you have a very light object with the flat surface, like for example feather or paper, at that moment, if you have air air effect, in other words, if you have air resistance for doing this experiment, at that moment air resistance will affect your flat object. For example, if you have feather or if you have paper, you have the same problem here, and they don't follow those equations regarding falling object. But of course, brick or hammer will follow those equations. Consequently, if you have a very flat surface, and you have very light object, and if you want to do this experiment in the air, of course, air resistance causes much difference between these two objects. And at that moment, you will observe this difference during this experiment. And of course here for this feather, here, because of the air resistance, it is much slower than brick. In general, if you have air resistance and you have very light object and its surface is flat, at that moment, falling object equations are not valid for this specific material or for this specific sample. It's important. But right now, imagine we are close to the moon surface. And you know that the moon surface, on the surface of the moon, there is no air, or you have vacuum. And if there is a vacuum around your experiment, at that moment you don't have air resistance. And if you don't have air resistance, in other words, if you have vacuum at that moment, there is no difference between two objects. I mean the hammer and the feather, or brick and hammer. And if you drop these objects from the same time and same height, they have the same velocity and they have the same time of falling. And that's the point. And the answer of this question is related to this factor, air resistance. If you're close to the earth, you have air. And air causes much difference between these two falling objects. On the contrary, if you're close to moon surface, because of vacuum and there is no resistance, air resistance, they're going to be the same. And they have the same time of falling. If this person wants to travel to the moon surface and would like to perform this experiment one more time close to the moon surface, at that moment, he will observe they're going to be the same. It's very important. Okay, let's switch to the note. Therefore, here, if you have air resistance, these equations are not valid. Sometimes it happens for falling object if it has very high velocity. And for that moment, these equations are not valid for very high velocity. For example, if you have like you have condensed mass and you want to shoot it downward, but it has very, very high velocity. Again, these equations are not valid for this object. And your equations are different from the classical equations. This is not the scope of this course. It should be discussed in advanced physics. Okay. Now, I want to talk about projectile. Okay. Look at this one. Imagine there is a particle here. This is the level of the ground here. if you want to shoot this particle with initial velocity and an angle with respect to horizontal line, imagine it's here. This is your initial velocity, v0, and you have angle here, this one, this angle. If you have this kind of motion in the space, at that moment you have this kind of trajectory. Look at this curve. So it's not very good. We'll modify it. This one is better. This object is projectile, and this motion is called projectile motion. And it has many applications. Okay. I want to discuss the velocity and acceleration here. Look at this coordinate here. This is my origin. For better understanding, I prefer to put it here because I want to show you everything clearly. This is X. Sorry, this is X. This is Y. Unlike the rectilinear motion, over here you have two variables. The first one is X and the second one is Y. But remember the rectilinear motion in the first lecture, you need only X variable for rectilinear motion. Or for vertical motion, like free fall, you need only Y variable. That's vertical. But for projectile motion, you need both variables, X and Y, at the same time. Because over here, you have X motion and Y motion, both of them. For horizontal rectilinear motion, you need only X axis because you have X motion. For vertical motion or free fall, you need only vertical motion, or you need Y motion, which is Y axis. Over here, you need both of them because you have X motion and Y motion, meaning that this object is going to the right. Of course, it's going to the right. But if you switch to Y-axis, you can observe it will go up and it will go down. See, it will go up to this to reach this point, and from here it will go down along Y. Therefore, you need two variables to describe this movement. Therefore, we need XY coordinate here. Okay, imagine this projected motion. I want to project the motion of the projectile along X-axis. I mean here. Only here, along this X. It is projected motion. Do you agree it is always to the right? It is always to the right. Okay, if I want to project this motion along Y-axis, what happens? If I project it along only Y-axis, you will figure out at first it will go up, and finally it will go down like this. This one is vertical motion here. Okay, this point here, it is the top of the curve. It is called maximum height. Maximum height of the projectile. And you know this path, it is called trajectory. Therefore, let's review it. Along x-axis, you have always a motion to the right. Along only y-axis, you have up and down motion. At first, it is upward motion. And if it reaches maximum height, it will go downward. Along x-axis, do you agree over here along x-axis, you don't have any gravity and you don't have any acceleration? Because you know gravity is related to vertical motion, not horizontal motion. Therefore, along x-axis, which is horizontal motion here, you don't have any accelerations. And you know from previous lecture that if there is no acceleration, you will have constant velocity. Therefore, along x-axis here, along x-axis, there is no acceleration. In other words, the projectile has constant velocity along x. Very important. Okay, let's focus on y-axis along y. It means you need projection. Along y-axis, project your motion along y. At first, you have upward motion, and that's vertical. And it can reach maximum height, and eventually it will go downward. Do you agree? It is vertical motion, and you know gravity is effective for vertical motion. It means here you have gravity or you have acceleration. And we discussed it before. I mean, if you have vertical motion affected by gravity, it is called free fall. Therefore, here you have a free fall or you have falling object. Consequently, projectile motion is combination of a constant velocity along x and free fall along y. Along x-axis, you don't have any accelerations. Along y-axis, you have gravity. And you can discuss it separately for x-axis and y-axis. Consequently, projectile has an acceleration, but this acceleration is gravity. Imagine your object is here. For example, one of the positions of your projectile is here on this curve. It should be on the curve because this is the trajectory of the projectile. Imagine it starts from this point. Of course, it can reach this, and it will follow the curve to reach the final position, which is here. if this is your projectile here, orange color, question, does it have acceleration? Of course, yes. The projectile has acceleration. What is the acceleration of the projectile? That's gravity. And you know gravity has direction. It is downward. Along y-axis, it is downward. This is the direction of acceleration or gravity. G. And you know it is along y-axis. Consequently, projectile is a kind of accelerated motion. It's very important. Thank you.